Hello, everyone. I'm Yuzhou Feng from the Florida International University in Miami. Today, my partner Qi will do the presentation with me for our paper. Our topic is the SolarFinder automatic detection of the solar photovoltaic arrays. So as we know, the smart grid is a network system that is comprised of over 500 million sensors and actuators. And it is also one of the largest Internet of Things deployment in the world. Refer to a report to the United States Solar Energy Industrial Association, we can see in the past years, the installation cost of the solar array decreased by 3 times. At the same time, the solar capacity increased by about 38 times. And 70% of the solar arrays are small-scale PV arrays, and they are installed on the residential roofs. There are so many implications in this rising solar penetration. For example, the utilities, third-party companies, and the governments are facing the same challenges on managing and controlling the intermittent solar energy. To solve this issue, there are some existing approaches. One of them is the online solar assistance. The benefit of this approach is that we can collect the more accurate solar array informations, but it also has several problems, such as it requires user expertise to report and file the assessment, and it also have a limitation in some geospatial resolution and hard to scale up. It's also very time consuming and costly. There are also some other approaches based on the machine learning and deep learning. The benefits of the machine learning, as shown in the table below, is that it reports a very high true positives, which means it can detect the solar arrays very well. But the deep learning approaches, it reports a high true negatives, which means it can has better performance to identify the non-solar array objects. But all these approaches have the problems such they require significant amount of the training data, and they require very high resolution images, and they also require human handcrafted image templates. So can we get both the benefits from the machine learning and deep learning? In another word, can we achieve the high true positives and the true negatives at the same time? And is that possible to only use the publicly available satellite images with a regular resolution rather than VHR images? So all these motivate us to design a new system named the SolarFinder. And we have 3 main goals for this new system. Firstly, we only want to use the public available low or regular resolution rooftop satellite images. And for our system, we want it to automatically detect the solar PV arrays in a given region without extra cost. And we also want our system to learn detailed installation information for each solar site. For example, the orientations and the size of the solar array. So here's the overview of the design of the solar finders. And my partner Qi will go to the details for each steps.
Hello everyone, I'm Qi. So you can see this pipeline from the left to right. We have 4 steps. And we can see the first step is we do the satellite images segmentation to get the rooftop images. Then we do the objects extraction. And then we use our hybrid classifier to detect the solar arrays from these objects. And at last, we can get the information like size and orientation. So now let's go to the details. So the first step is extracting rooftop images from satellite images. Well, you can see this pipeline. Given a region, we first go to OpenStreetMap to get the rooftop polygon information, and we feed this information to the Google Maps. The Google Maps can return segmented rooftop images. So by doing this, we can filter out other outliers like trees and roads and focus on the rooftop images only. Well, the next step is extracting rooftop objects. As you can see in the figure, we leverage k-means algorithm to automatically segment the rooftop image, while k-means assigns each pixel based on the grayscale value. The key challenge here is when we use the k-means, we need to know the k in advance. Well, to address this issue, we use elbow method to find the optimal k equals to 5. Then we need to identify the solar arrays among these objects. Here we design our hybrid approach. Look at this pipeline. We first empirically extracted features and then use PCA to get the principal features. We feed these features to the machine learning model. And we also train our deep learning model using the object's images. Then we combine the machine learning and deep learning to get the final detection result. Now let's look at the details. While we first select the best performing machine learning classifier, we investigate the current machine learning models. We found that the SVM classifier with the RBF kernel has the best performance. The next step is designing deep learning classifier. These figures show the whole architecture of our model. The input are the object's images, output is the prediction result. It has 16 layers. I wouldn't go through the details. Then eventually we combine the two models together using fusion approaches. Well, there are so many fusion approaches available. Which one we use? So we do a study. You can see this figure here. The linear regression gets the best result. And you can also see the final model as shown in this equation. Well, after we identify the solar PV arrays, we can characterize the installation details from the solar arrays, like size, orientation, and shadings. Well, this graph shows how we find the orientation. Basically, we calculate the angle difference between the bounding rectangle and the medium area rectangle. Implementation. We leverage Maps APIs to fetch the satellite images, use packages for image pre-processing, and use secular machine learning library, schedule the batch jobs on GPU servers. Next, I'm going to show you how we evaluate the SolarFinder. We do two different categories evaluation. Well, the first one is retrained approaches. So you may think about like, what is retrained? Well, basically, these approaches have access to the testing sites. So they can use the ground truth data from their testing sites to calibrate the model. As shown in this table here, the SolarFinder gets the best accuracy, and the accuracy already as 2 times as the pure CNN approach. Then we perform pre-trained approaches. Well, this time all the models do not have access to their testing sites. They do not have any piece of information from the testing sites. Well, just let you know, like in real application, SolarFinder works in a pre-trained way. Well, you can see this table. As expected, the SolarFinder is the best performance classifier. Actually, it has like accuracy as 3 times as the pure CNN approach. In addition, we can look together. You can observe that the pre-trained SolarFinder has the same accuracy as the retrained pure CNNs. Well, actually, we have much more evaluation. If you are interested, you can go ahead to check our paper. Eventually, we also try to integrate the SolarFinder results with the solar forecasting models. This graph can show 10 different houses before and after using our SolarFinder results. Well, as you can see, like SolarFinder is very helpful to have 10 homes to get a better forecasting accuracy. In conclusion, we designed a new system called SolarFinder, which can automatically detect the solar arrays, also profile the detailed installation information. And for future work, we are working on optimization for SolarFinder, and we also want to include accuracy under new situations, such as Tesla singles. Thank you very much for your time, and this is all my presentation. In addition, we also released the dataset and code to this link. Please let us know if you have any feedback. Thank you.